I want to recommend a book which named Bitcoin, a peer-to-peer electronic cash system. A purely peer-to-peer version of electronic cash would allow online payments to be sent directly from one party to another without going through a financial institution. Digital signatures provide part of the solution, but the main benefits are lost if a trusted third party is still required to prevent double spending. We propose a solution to the double spending problem using a peer-to-peer network. The network timestamps transactions by hashing them into an ongoing chain of hash-based proof of work, forming a record that cannot be changed without redoing the proof of work. The longest chain not only serves as proof of the sequence of events witnessed, but proves that it came from the largest pool of CPU power. As long as a majority of CPU power is controlled by nodes that are not cooperating to attack the network, they'll generate the longest chain and outplace attackers. The network itself requires minimal structure. Messages are broadcast on a best effort bias, and the nodes can leave and rejoin the network at will, accepting the longest proof of work chain as proof of what happened while they were gone. Commerce on the internet has come to rely almost exclusively on financial institutions serving as trusted third parties to process electronic payments. While the system works well enough for most transactions, it still suffers from the inherent weakness of the trust-based model. Completely non-reversible transactions are not really possible, since financial institutions cannot avoid mediating disputes. The cost of mediation increases transaction costs, limiting the minimal particle transaction size and cutting off the possibility for small casual transactions. And there is a broad cost in the loss of ability to make non-reversible payments for non-reversible services. With the possibility of reversal, the need for trust spreads. Machines must be wary of their customers, hustling them for more information than they would otherwise need. A certain percentage of fraud is accepted as unavoidable. These costs and payment uncertainties can be avoided in person by using physical currency, but no mechanism exists to make payments over a communication channel without a trusted party. What is needed in an electronic payment system based on cryptographic proof instead of trust, allowing any two willing parties to transact directly with each other without the need for a trusted third party. Transactions that are computationally impractical to resolve would protect sellers from fraud, and routine escrow mechanism could easily be implemented to protect buyers. In this paper, we propose a solution to the double spending problem using a peer-to-peer distributed timestamp server to generate computational proof of the chronological order of transactions. The system is secure as long as honest nodes collectively control more CPU power than any cooperating group of attackers' nodes. We define an electric coin as a chain of digital signatures. Each owner transfers the coin to the next by digitally signing a hash of the previous transaction and the public key of the next owner and adding this to the end of the coin. A payer can verify the signatures to verify the chain of ownership. The problem, of course, is the pay can't verify that one of the owners did not double spend the coin. A common solution is to introduce a trusted center authority or mint that checks every transaction for double spending. After each transaction, the coin must be returned to the mint to issue a new coin, and only coins issued directly from the mint are trusted not to be double spent. The problem with this solution is that the fate of the entire money system depends on the company running the mint, with every transaction having to go through them, just like a bank. We need a way for the pay to know that the previous owners did not sign any earlier transactions. For our purpose, the earliest transaction is the one that counts, so we don't care about later attempts to double spend. The only way to confirm the absence of a transaction is to be aware of all transactions. In the mint-based model, the mint was aware of all transactions and decided which arrived first. To accomplish this without a trusted party, transactions must be publicly announced, and we need a system for participants to agree on a single history of the order in which they were received. The pay needs proof that at the time of each transaction, the majority of notes agreed it was the first received. The solution we propose begins with a timestamp server. A timestamp server works by taking a hash of a block of items to be timestamps and widely publishing the hash, such as in a newspaper or answered post. The timestamp proves that the data must have existed at the time. Obviously, in order to get into the hash, each timestamp includes the previous timestamps in the hash, forming a chain with each additional timestamp reinforcing the ones before it. To implement a distributed timestamp server on a peer-to-peer basis, we will need to use a proof-of-work system similar to Dan Black's Hashcash rather than newspaper or Usenet posts. The proof-of-work involves scanning for a value that, when hashed, such as with SHA to 256. The hash begins with a number of 0 bytes. The average work required is exponential in the number of 0 bytes required and can be verified by executing a single hash. For our timestamp network, we implement the proof of work by incrementing a node in the block until a value is found that gives the block hashes the required 0 bytes. Once the CPU effort has been expanded to make it safety, the proof of work, the block cannot be changed without redoing the work. As later blocks are trained after it, the work to change the block would include redoing all the blocks after it. The proof of work also solves the problem of determining representation in majority decision making. If the majority were based on one IP, just one vote, it could be subverted by anyone able to allocate many IPs. Proof of work is essentially one CPU, one vote. The majority decision is represented by the longest chain, which has the greatest proof of work effort invested in it. If a majority of CPU power is controlled by host nodes, the host chain will grow the fastest and outpace any competing chains. To modify a past block, an attacker would have no redo the proof of work of the block and all blocks after it, and then catch up with the subpass, the work of the honest modes. We will show later that the probability of the slow attacker catching up diminishes exporting as subsequent blocks are added. To compensate for increasing hardware speed and verifying interest in running nodes over time, the proof of work difficulty is determined by a moving average, targeting an average number of blocks per hour. If they are generated too fast, the difficulty increases. The steps to run the network are as follows. First, new transactions are broadcast to all nodes. Second, each node collects new transactions into a block. Third, each node works on finding a difficult proof of work for its block. Third, when a node finds a proof of work, it broadcasts the block to all nodes. Fifth, nodes accept the block only if all transactions in it are valid and not already spent. Sixth, nodes express their acceptance of the block by working on creating the next block in the chain using the hash of the accepted block as the previous hash. Nodes always consider the longest chain to be the correct one and will keep working on expanding it. If two nodes broadcast different versions of the next block simultaneously, some nodes may receive one or the other first. In that case, they work on the first one they received, but save the other branch in case it becomes longer. The tie will be broken when the next proof of work is found and one branch becomes longer. The nodes that were working on the other branch will then switch to the longer one. New transaction broadcasts do not necessarily need to reach all nodes. As long as they reach many nodes, they will get into a block before long. Block broadcasts are also tolerant of dropped messages. If a node does not receive a block, it will request it when it receives the next block and realize it missed one.